So I'll be talking today, as Stacy mentioned, about the Rosetta mission, which was a European Space Agency mission, but there was quite a bit of NASA contributions to it. So it really was an international collaboration, and it was quite an honor from the NASA side to be able to be a part of this mission. So I'll tell you a little bit about myself first. I am an interdisciplinary scientist. That means that I do research that focuses on a large range of topics. I work in chemistry, I work in physics, I study atmospheres, I study interaction of atmospheres with planet surfaces. And this is one of the aspects of being a planetary scientist. You really have to go beyond a single discipline to be able to understand the planets in our solar system. I took a very non-traditional path to get to this point. When I graduated from high school, I didn't have the resources to be able to go to college, so I joined the military so that I could take advantage of the GI Bill and help pay for my college eventually later. I was interested when I joined the Navy in being a nuclear physicist, but at the time that I joined, women were not allowed to serve on combat ships, and all of our nuclear reactors are on combat ships. So women were excluded from that career path at that point in time. Things have changed now, and women are able to be part of that career. But because of the timing, I wasn't able to do it, and so I became a Russian linguist, and I spent 7 years in the military. I traveled all over the world as part of the military and then as a Navy spouse, and ended up being a stay-at-home mom for about 10 years because when you're traveling all over the world, it's very hard to complete a PhD. But eventually I was able to complete my education and start working on some NASA and ESA missions, which has been quite an honor and an opportunity for me. And Stacy's already covered the different missions that I've been able to work on. Now I am able to see the Q&A on a different screen. So if you type in a question, I'll be able to see that you have asked a question. So go ahead and feel free to use that if you're able to find it. Okay, so moving on to the science side of things, my research focuses on looking at volatiles throughout the solar system. And volatiles are molecules and gas species that end up being gas at room temperature here on Earth. So the surface conditions on the Earth, they're the kinds of components that end up being in the atmosphere. And what I do is I take measurements in the present day of comets and atmospheres and planets and look at what we can learn about the history of the formation of the solar system from these measurements. And the Rosetta mission was a very important mission for that kind of science. In fact, I'm still using data from the Rosetta mission to continue this research, even though the mission is no longer active, which I'll get to towards the end of this talk. So the Rosetta mission is designed, or it was designed, to decode the history of the solar system and led by the European Space Agency. They named it after the famous Rosetta Stone, which was a rock where they found the same text written in 3 different languages. And the Rosetta Stone was a groundbreaking opportunity for decoding writing in these 3 different languages because they had the exact same text in the different languages. And the purpose of the Rosetta mission was similar, to look at a time capsule and decode the history of the solar system from studying a comet. The other thing that the Rosetta mission did was to try to understand comet activity. And I'll talk a little bit about both of these, some of the results that we got from that. The mission was made up of a spacecraft and a lander. The spacecraft had 15 instruments on it, and 2 of them were contributed by NASA. And then the lander had 10 instruments. And I'll talk a little bit about both of those as well. My part on this mission was working on the ion electron spectrometer. It was IES, and that was contributed by NASA. And it was part of a consortium of 6 different instruments, or actually 5 instruments, and then a computer that connected the 5 instruments. So we had teams from 4 or 5 different countries working together throughout the entire mission, sharing a computer. So we had to work together to plan our operations. And then because we worked well together, we also shared data, and we worked together on understanding the environment of the comet and publishing papers together. So it was a really wonderful experience to work with such a unique team. We would go to meetings in different places in Europe, and there could be 10 to 15 different languages represented by the people in the room. And it was exciting being in that kind of dynamic and unique environment. I also worked with another instrument that was called the Rosetta instrument. It's got 3 components to it. And the component that I worked with the most, and I'm still working with, is this one, which was measuring the composition of the gas around the comet. What it would do, it would take some of that gas into the instrument and separate it out by the different molecular species and figure out what was there. So we called it the one that was sniffing the cometary gases. And a lot of important results have come out of that instrument. Now, the missions like Rosetta and missions to the outer planets, anything to Jupiter and beyond, really take a long time because it's farther out. What I'm showing here is a graphic that illustrates the journey after launching from Earth to get to the comet. The spacecraft was launched in 2004 and had to do gravity assists using the Earth and Mars at 3 different times. And that changed the trajectory of the spacecraft. You see the comet is appearing now. It changed the trajectory so that the spacecraft could eventually catch up with the comet. Now, when it got beyond the orbit of Jupiter here, they had to put it in hibernation and wake it up again later because it was too far from the sun for the solar panels to provide enough power. It did arrive safely at the comet in 2014, and we had a wonderful mission after that. So hibernation for a spacecraft worked, and it was one of the first times we tried doing that. It took 10 years to get there, though. So when we arrived at the comet, we started looking at it from a distance because we knew where it was, and we used the camera to kind of make sure that we were on the right trajectory. So as we approached, we started taking pictures of the comet and studying it. Before we got close enough to start taking pictures, this image here is what we were expecting the comet to look like. And it was based on Hubble Space Telescope observations, which were the best that we could do at the time for imaging such a small object so far away from the Earth. But as we got closer, we saw a very different looking comet. You'll notice here that we are seeing the comet from multiple sides. That was because the comet rotates just like the Earth rotates and has night and day, and then it's tilted to the sun. So it also has seasons, just like the Earth has seasons. The timing is different and the seasons are different, but it's very similar in that way. So we got to see pictures of the whole comet, and we were quite surprised and entertained at how the comet looked like a rubber duck. So we had a lot of fun with our rubber duck comet. Here's an image of the comet up close, and then another decorated image of the comet. And then another thing that we would do as we were studying the comet, we would make little models of it so that we could perhaps hold it up to a light and figure out what parts were being lit up and what parts were in shadow. So of course we had fun with those models of the comet as well. We have the little mother duckling and the mother duck and the little ducklings following. So we had a really wonderful team, and we really had a wonderful mission that was a lot of fun with this. But getting back to the science, there was some surprising science as well, not just how the comet looked, but we also found some unexpected observations with the other instruments. That one that I talked about before that was sniffing the gas of the comet, as it was approaching, it noticed that it wasn't just a solid mixture of water and carbon dioxide and carbon monoxide. We were expecting to see these things, but we weren't expecting to see them increasing and decreasing in a periodic way with the rotation of the comet that was facing the spacecraft. And what we found that there were times when there was more water than carbon dioxide and carbon monoxide. And then there were other times where carbon dioxide and carbon monoxide were dominant. And this was a big surprise, showing seasonal effects and an area of the comet that was exposed and releasing some gas that was from a deeper part of the nucleus. And these observations we were able to use to get a better understanding of what the ices were like. And some of the ices that are inside the comet are a thing called clathrates. Clathrates are really interesting because they're water ice, but the water forms these cages where they can trap other things inside the cage. So what we're showing here is a clathrate that is trapping carbon dioxide in it. So we were able to learn quite a bit about the comet itself as we approached it. Once we approached the comet, one of the first things that we did was we had the lander, and we were going to land that lander on the surface of the comet and take observations very close to it from the surface. But this had never been done before, so there was a lot of work that needed to go into planning the lander itself. So what we did was we did orbits where we did mapping, complete mapping of it, and then we picked different sites that we wanted to determine which ones we wanted to use. So what we have here is a illustration of the mapping of the comet and then the landing process. Now, the gravity of the comet itself was really low, so it's not a big enough comet for us to orbit without having to use the engines to change the trajectory and keep close. So the operations of the spacecraft was challenging all the time. Here we are when we arrived, and we were getting close in to about 10 kilometers from the comet. The comet itself is about 2 to 4 kilometers across. And we just kept going around it and taking lots of different pictures. And then when we decided where we wanted to land the lander, the way that we did it was we suddenly turned in towards the nucleus and almost looked like we were going to do a crash landing, turned away, dropped the lander, and then the lander went down to the surface. And then we continued orbiting around the comet to try and trap the lander and communicate with it so that we could get the data that was coming from it. Now I'm going to move on to the next slide, which tells you a little bit about the lander. Because, as I mentioned before, the gravity of this lander is not very strong. It's a weak gravity, so it'd be very easy for the lander to not stay put on the surface. So there were two mechanisms that were designed with this lander to make sure that it stayed in place once it landed on the surface. One of those was thrusters that were on top of the lander. They would fire upwards to push the lander down towards the surface. And then on the bottom, there were a couple of harpoons that were going to fire into the surface to physically attach the lander to the surface so that it wouldn't float away. Now, we spent 10 years in space with the spacecraft after leaving Earth. And when we got to the comet, we checked the conditions of the lander. And one of the things we found was that there were problems with the thrusters on top of the lander. And we knew before going into the landing that the thrusters were probably not going to work. But it was worth trying to do the landing anyway, because we were already there. There was no way to fix it. And the science potential of any data that we could get was worth achieving. And we were hopeful that the harpoons would be able to fire into the surface and hold the lander in place, and that would be enough. So what actually happened was that The harpoons also did not work. They did not fire into the surface. And so when the lander landed, it bounced and then landed again and then bounced and landed a second time. So we landed 3 times on the comet. We were able to take images of the comet in the area where the lander went down. So we were actually able to go back and see the lander itself around each of those times when it bounced, and we were able to find some of the footprints of it, like where it actually hit. Like you can see the footprints of the lander here before and after. And then we were able to find where it was located eventually after it finally landed. Now, when we got onto the surface, we had an instrument called MUREP that would pound on the surface. And it doesn't sound scientific to be hammering the surface and just seeing what you find. But there was a scientific reason for hammering into the surface, because we wanted to know how hard the surface was, because we've never landed on a comet before. We don't know if it's all a bunch of fluffy powder that will spray up everywhere, or if it's solid like a rock. And what they found was that it was very, very solid. They were not able to break through the surface with the hammer on the lander, which meant that if the thrusters had, or if the harpoons had worked, the lander would have shot off of the surface of the comet and never come back down. So we got lucky that the harpoons did not work, because that could have been disastrous for the mission as well. Now here's what the lander was able to see once it landed on the ground. These are the different cameras that we had. And when we looked at the images from the camera, we were really excited by these two, because they were showing the surface, and this was showing some of the surface as well. And then we were a little disturbed by this one, because it showed the sky, and it wasn't supposed to show the sky. It was supposed to show the surface if the lander had landed upright. And what that showed us was that the lander had landed on its side. So part of it was looking at the sky. Later, we were able to locate the camera with the locate the lander with the camera on the orbiter and take images of it. And we could see a leg was sticking up and it was on its side. But we still got some really amazing data from the lander that led to several publications and a lot of really cool results. Now, after the landing, the mission wasn't over. The mission actually continued for 2 more years, with the orbiting spacecraft following the comet all the way through its trajectory as it went around the sun and came back out. So we continued and took a bunch of measurements. One of the measurements that was really interesting was with that instrument that I mentioned before that was sniffing the gases in the comet. They found some really interesting compounds, like stuff with sulfur in it and nitriles and amino acids. And one of the things that they did for outreach was they took these compounds and figured out what they would smell like, and then they made postcards that would smell like what the comet would have smelled like. And they were very pungent. They were wonderful to bring to schools for outreach activities, but boy, my entire backpack would stink because of those postcards. So the comet itself is pretty stinky. We also did close mapping of the comet and tried to understand how the comet formed and tried to look at comet activity. What I'm showing here is an outburst. And this was something that was really interesting. We saw several times where the comet will release gas as it approaches the sun because it gets warmer. But sometimes there's something that becomes unstable in the comet, and it just it sends out this burst of gas and dust that were glowing in the camera view. So that it was really beautiful. It was like fireworks, but out in space. Now, the comet changes how much water it's producing and how much of a coma it is creating as it approaches the sun and as it goes away. So I'm showing here the orbit of this comet. we arrived around this time where there wasn't much of a coma at all. This coma is the gas and the dust that surrounds the nucleus of the comet. And as we got closer, there was more and more activity and more gas coming out. Now, this gas is coming out pretty fast because once the water gets heated up and it turns from ice to gas, it just wants to go away. So it spreads out and then it spreads away from the sun because the radiation pressure of the sun just pushes it away from the sun. And that was really interesting to be observing, but it was also an interesting environment to be operating a spacecraft, in particular a spacecraft that has solar panels that function like wings in a wind that is coming from the comet. So we had to learn how to operate this spacecraft in an environment that was constantly trying to push the spacecraft away from the nucleus, and that was very fascinating. And it was also challenging. So we saw during this time, we got to see a whole bunch of outbursts, and we also saw a lot of dust. Now, that dust ended up being a problem that nobody really predicted, and we, in hindsight, should have. One of the ways that you control a spacecraft is you use a star tracker, and a star tracker takes images of the sky, identifies the stars in that image, and figures out what direction the spacecraft is pointed in based on the stars that are in the view of the star tracker. And that is an important way to make sure that the antenna is always pointed to the Earth, that the solar panels are pointed to the sun so that you continue receiving power, and that you're moving in the proper direction. And one of the times when the comet became much more active, we did a close flyby into the comet. We started at a distance, flew in close, and we tried to get pretty close. But as we got in, this is what the spacecraft star trackers saw. And this is a lot of dust that is lit up by sunlight. And that dust looked like stars. And the star tracker became confused. So the spacecraft became confused and shut itself down. Now, when we design spacecraft, we design them to shut themselves down in a situation like this. We call it safing a spacecraft. We make sure that the spacecraft is safe above all else. So what happened was the spacecraft safed. It continued to move in its direction. It turned back on, figured out the direction it was pointed back to Earth and to the sun, and started communicating again with Earth. And we learned from that we needed to have more caution in the way that we operated the spacecraft in this environment. So getting back to my research, we got observations of noble gases in the comet. This is the only comet where we've been able to measure krypton and xenon and argon. And these are really interesting because they help me to piece together whether ice or rocks formed things like Jupiter. And so this is some of the research that I'm continuing to do with the measurements that we've got from this mission. I also take measurements of isotopes. Isotopes are atoms of they're different atoms, like hydrogen has two isotopes. It's hydrogen and then hydrogen with an extra neutron in it that makes it twice as heavy. So they're the same species, but different mass. And we use that information to track the origin of species that are located in atmospheres or the origin of materials that are on the surfaces of planets and moons. And so this is also ongoing work that I'm doing. Now, the mission ended in 2016, and we had 3 different options that we considered for ending the mission. One of them was to exit the spacecraft down the tail of the comet and just go off into space. Nobody had ever sent a spacecraft into the tail of a comet, so we were really interested in possibly doing that. We also considered going back into hibernation, following the comet around again, and then trying to wake the spacecraft up. That was a pretty high risk thing because we didn't know if we would remain close to the comet or if we would drift away when we were in hibernation. And then the other option was to just land on the comet again, this time with a spacecraft. And that was what we chose to do. So we had a second landing, and that's where we ended up disposing of the spacecraft because we didn't want to leave it just out in the open or leave it in space with no direction. This way we were able to get more science out of it. So that was the end of the journey.